All right, let's move on to the next question. So, this is LeetCode number 134, gas station. There are n gas stations along a circular route where the amount of gas at the ith station is gas I. Okay. You have a car with an unlimited gas tank and a cost of sub I of gas to travel from the ith station to its next I+1 station. You begin the journey with an empty tank at one of the gas stations. Given two integer arrays, gas and cost, return the starting gas's index if you can travel around the circuit once in a clockwise direction, otherwise return -1. If there exists a solution, it is guaranteed to be unique. Interesting. Let's look at the example. So, gas 1, 2, 3, 4, 5, which is how much gas we have, and the cost to get to the next location. Okay. If you start at station 3, you fill up 4. You fill it with 4. You travel to station 1, subtract 1, and you get 5. Because it costs 1 to get to the next station, and you get 5 at the next one. Cost 2 to go to there. You get that and that. Okay. Okay. Interesting. And then, as always, input. Check the input to see if we can get an estimation of time constraint. This is an O of n solution because n is less than or equal to 10 to the 5, so it's probably roughly O of n for our optimal solution. Let's see. That means that we have to start. We can't simply check each one. So the naive solution is to say that we can't, or we start at each and check if it works. Right, so you start at index 0 and you see if you can get back to index 0. Index 1 and you see if you get back to index 1. That will take O of n squared time if we start at each station and then try to loop back in the worst case scenario. Of course, you'll probably fail somewhere along the way, but that's besides the point. It'll still be around O of n squared runtime if we're checking to see if we can traverse n items starting at some given item in the middle. So perhaps a better solution, if we're using O of n, well, I think the problem here is that we can't just check to see if we can reach a gas station from the previous, because we might have an accumulated amount which can actually pass to the next station. And what I mean by that is that, for example, let's see if example 1 has it. For example, going from gas station 1 to 2, it costs 3. Of course, this gas station only gives you 1. However, you actually have a bunch of left over from the previous stations that help you get to where you need to go, right? So it's not just saying, can we reach one place to another in that way. Let me think. I'm thinking about 2 pointers potentially. Or some sort of, yeah, some flavor of 2 pointers, right? Either regular 2 pointers, fast and slow pointers, something like that, in order to basically check to see. But how would that help us, right? Maybe a greedy approach? What I'm imagining is start with a linear scan, check to find the jump with the most leftover in a raw way. So what I mean by that is that we'll check, okay, the cost to go from 1 to 2 is 3, and you get 1. Or 0 to 1. 0 to 1 costs 3 and you get 1. That's a cost of -2, or that's a gain of -2. Going from 1 to 2 costs 4, you get 2. That's -2. Going from 2 to 3 costs 5 and you get 3. That's -2. Cost to get from 3 to 4 costs 1 and you get 4, so that's a +3. And cost to get from 5 to 0 is 2, and you get 5 back. And you get 5 back, so you get a you get a profit essentially of 3. So both of these paths seem to be viable. But how do we choose the one? We want to choose the one that is the earliest viable. I think, because then if you choose the earliest viable option, then you know that you will start with a surplus, and you hope that the following items won't screw you over. The following gas stations won't screw you over. That could be potentially a way to solve this. The problem with greedy solutions is not proving the runtime, because I mean, you do a linear scan here, it's not a big deal, and then you just choose the earliest viable option. That's not a huge deal. That's like an if statement, and then you just scan through the rest of it. It's very clearly O of n time. The problem with greedy solutions is not proving the runtime, it's proving the correctness. And in this case, proving the correctness of a greedy solution is always a pain to deal with. And so this might be an interesting option, but it's certainly not the first option that comes to mind in order to really be correct. It'll work for gas station, for example, 1, but I'm not sure if it'll work for all cases. But I don't think that 2 pointers affords us with anything that is worthwhile. So I think I'm going to remove this off of the realm of possibilities. Let me see if I can think of this as like a graph problem, right? So suppose each node is a gas station, and each edge is a road with a weight cost. So it would be like A to B to C to D, and then back to A, essentially. So 1, 2. Where A to B is equal to 3, B to C is equal to 4, etc. Well, in this case, since there's always an incoming edge to all of them, we can't use a topological sort. Since we essentially have a circle of incoming edges, right? There is no node in here which does not have an incoming edge. So there's no topological sort. We can't run DFS at each one, like we said, or BFS, whatever. It's the same thing because it's just there's only one incoming and outgoing edge, right? So it doesn't really matter which algorithm you use. Honestly, I am tempted to try out the greedy solution and see if it works. Like, it seems kind of stupid to choose the earliest viable option, but at the same time, I feel like I just have with a weird gut feeling that, like, hey, this might not be as stupid as it sounds. Or maybe it is as stupid as it sounds. The only way to really know is to give it a try and see if it works. Do I have any other solutions off the top of my head currently? We don't need a contiguous subarray, so it's not sliding window probably. We can't really manipulate the data because we need to go in order, so we can't sort it. There's nothing that we can accomplish with sorting. And honestly, let's see. Is there a sub-problem that exists within here? No, there really isn't a sub-problem that exists within here because going from 4 back to 4 does not involve going from going from 4 to 4, or like for example index 3, so 0, 1, 2, 3, going from 4 to 5 to 1 to 2 to 3 to back to 4 does not involve going from 3 to 3 or something like that, right? It does involve going from 4 to 5 and then 1 to 4. But we need the information. We need the information from the previous subproblem. So there's very clearly an overlap of subproblems because we need the context from the previous subproblem. We need the context from the trip from 4 to 5 in order to solve 1 to 3 or 1 to 4, right? Because we need the amount of surplus gas in order to really make a decision on whether or not that route is viable. So there are the problems are kind of overlapping, which makes me think potentially a dynamic programming approach might work. But all the dynamic programming graph single pair paths or like connectivity paths algorithms seem to be running, as far as I recall, seem to run in polynomial time. Let me think. Suppose we did do that. So we had 1, 2, 3, 4, 5. And we had starting at 1, starting at 2, starting at 3, starting at 4, starting at 5. Of course, starting at 1 to 1 will cost 0. Same with 2 to 2, 3 to 3, 4 to 4, 5 to 5. 1 to 2 will require a deficit of -2. 2 to 3 will cost a deficit of -2 as well because cost is 4. You only gain 1. Actually, 1 to 3 1 to 3, let's see, -2. So this will be -4. Right, because it'll cost you 2, so you get 1, subtract 3, so you're on -2 as you enter here. You get 2 back, so you're at 0, and you get minus 4, so you get -4 as you roll into station 2, or station 3 rather. So you gain back 3, so you get -1 plus 1, that's -2 again. And then here you get 5. Or rather, it's like, to get to 2, once you get to 2, you're at -2. Once you get to 3, you're at -4. And then once you get to 4, you're at -2 again. Because it takes 3 and 5. Then you get 4, you pay 1. So that should be -2. But in any case, if we did a dynamic programming approach, it would probably take polynomial time, which is not what we want. So the only really viable solution that I can see right now is the greedy approach that will take less time than that. So I'm going to go ahead and code it up, and then we'll see if it's correct or not. And then if it is correct, then we can prove, then we can spend some time to prove that it is. And if it isn't, then we'll be given a counterexample by LeetCode's test cases. But let's go ahead and give it a shot. So we'll say gas, well, we'll say this, gas.forEach. Or actually, we'll do for index in 0 to gas.size, -1, because gas and cost size are the same. We can say if gas at index minus cost of index is greater than 0, then we can break out from here, from this for loop, and we can say var start is equal to -1. Start is equal to index. Then we can say, so this requires O of n to find the first viable starting point. Then for index in start until while start is not at start again, or while the start plus 1 is not at start. Origin. We're going to be manipulating start, and we're going to be checking that against origin. We can say var gas amount is equal to gas at start. gas amount is equal to gas at start plus 1 minus cost at start, and then start plus equals start plus 1 mod gas dot size, I think. So that way we wrap around. If gas amount is equal or is less than 0, return -1. Otherwise we return start, because we assume that if we pass this loop, then we have made it. So we start at our first viable point where we can get a profit in our gas amount, and then we continue from there. The more that I think about it, the more I feel like this is not going to work. Because I can imagine having a viable starting point, or quote unquote early starting point, let's see, print line going from start to start plus 1 mod gas size, print line current gas amount. Because we can have a viable starting point, a really steep cliff that can't be beat, plus equals. A really steep cliff that can't be beaten by a current amount, and then like more viable options to start. In this case, we want to return origin. If gas at start minus cost at start is greater than 0, or gas amount plus. So basically at the end we want to see if we can actually make it back. If this, then start or origin, else -1. Greater than or equal to 0. Current gas 2, and then we go from 2 plus the amount that we get at 0, 1, 2, so 3. That's 5, which is 5. The cost is 5, so we barely make it back to the third gas station, and we're good to go. However, I can imagine if we had like a really diabolical situation, like let's see. If we had a gas, like, let's do 505 with a cost equal to 504, right? And if we check, Well, in this case, oh no, it won't stop there. No, but we could do something like this. And the cost is 4, but you don't get any gas here. Or you do something like that. There you go. So you start here because the gas is 5 and the cost is 4, right? So you can make it to the next station no problem with one tank left, with one unit left. But here you get none and you have to use 2, which is impossible. However, if you started here at the end, then you would get 1 left over to at arriving here, right? And then you'd use another one, or you'd get another surplus once you hit here, and then you'd have barely enough. So this would actually break. This would actually be a counterexample. 505. How did they model it? Okay, 505 and 424 would actually be a counterexample to my greedy choice. Because we would start at 0, right? 0 to 1 and then 1 to 2, which would not work. But technically it would work if we started at 2. So I wonder if, well, in this case we want to start at the earliest one, right? We wanted to start at index 4, which is the first one that has a gas surplus of 3, or well, a gas surplus of more than 0, right? So that's where we wanted to start. But in this case, we wanted to start at index 2, even though the gas surplus is the same for that. This maybe a greedy choice works, but I'm just choosing the wrong thing to be greedy about. Maybe it's not about the surplus. Maybe you want to find the start of the longest positive chain. But how do you find the longest positive chain in an amount of time that isn't stupid? Let's see. We can say and start is not equal if the start no, but then the start amount, because the thing is that this one, the start kind of crosses boundaries, right? It's not technically at the latest time, but this is like the earliest area of the chain. if the start well, we will always be going left to right, right? So what if we went backwards instead? So for gas.size minus 1 down to 0, index in, if gas index minus cost index is greater than 0, and in this case, because we're starting and we're going clockwise, we always want the start to be the one to the left. So, but we still run into the same problem from here, right? Let me give it some more thought, because we're at 30 minutes, but let me give it some more thought off camera. If I can't think of anything, then I'll just jump to the solution. But I feel like this might be it. Like, we just need to figure out, like, where the start of the longest chain of positive surplus gas is. Damn, I was close, but not quite. And the solution still revolves around a lot of math, to the extent that it's still a little bit confusing to me, but I'll try my best to explain it to you now. So the first part is pretty simple. We know that if a cycle that starts anywhere cannot get back to itself, basically if the sum of all the values and all the costs is less than 0, then a path is not possible. I think that's pretty straightforward in terms of what it's asking, right? So basically, can we complete the cycle? If not, then we don't even need to check whether or not, like, where a cycle begins, because we don't need to. We know that it doesn't matter where it starts from, this cycle cannot be completed. The second part, in terms of choosing the starting point, is a lot more complicated. So we'll walk through this step by step. So first, we have two outer variables, a starting point, which we will initialize at 0, and a current fuel, which represents the amount of surplus fuel that we currently have. It is at minimum a 0 because of the conditions inside our loop. Let's go inside our loop. So we will iterate through every single value within either of our arrays. I decided to choose gas. It doesn't matter which one you choose. It just needs to be indexed. We will check to see if our current fuel plus the value that we gain from our current gas station minus the cost to get to the next gas station is less than 0. If that value is less than 0, then we will move to the next gas station that we can after the index, and we will reset our current fuel because we assume that we start from that station. Otherwise, we just hold on to our current start point and we add to our current surplus of fuel. At the end, we will return start. Now here's where it gets tricky, because I think the main point of this loop and the main question that I had is, when we go through this loop and when we check and we move our index to the next gas station after we realize this one is not viable, how do we know that we have exhausted all options, right? And to a certain extent, I still don't really quite get this, so take my explanation with a grain of salt. But what I will say is that, let's suppose that, well, this is not supposing, but we know that the current amount that we have, the current result that we will get from this if statement, is the sum of all of our fuel stations that from, let's say, A all the way to some value K, as well as all the costs from starting from A all the way to that value K. Now we know that after we added K in terms of our station and our cost for some value of K, that this value is now less than 0. And now we want to say that we can just move our next possible starting point to K plus 1. How can that be? Well, how can we just skip all of the values between B all the way to K, essentially, B all the way to K, and just say that the next viable gas station is K plus 1? Well, remember that we chose A as our starting point primarily because of the fact of this same if statement, this same choice, that this same condition, that our initial starting point, the amount of gas that we get is less, or sorry, the amount of gas that we get is greater than the cost to move to the next station. Because if that were false, then we would have started at B instead. So we know that A, the gain that we get at A is greater than the cost to go from A to B. And because we know that that is true, then we know that by taking out A from our gain and taking out A to the cost of going from A to B from our sum of costs, that our solution will be no better. It will not, by removing A from our gain, from our surplus gas, and our A from our cost, the resulting sum will still be less than 0. Because fundamentally, the gain of A, the surplus of A minus the cost of A is greater than 0. So by subtracting it, we will either have not changed the amount, or it will actually be worse. So the solution that we get from the sum from B to K minus the cost from B to K will be no better than if we had A in the first place. And because that is so, then we can, I guess, in a way, disregard all the values between B and K in terms of viable candidates for our gas station, for our next choice of gas station. I'm probably butchering the explanation a decent amount, but that's sort of a high level of just me taking a swing at it in 10 minutes trying to figure it out. And this explanation and this solution came from this user, Pigwall. This is just the top solution, I think, within Java, and then I translated it to Kotlin. But yeah, the hardest part of greedy solutions, and I'm happy that it seems like for a lot of these times where I have to look at the solution, I'm on the right track. I just can't fully connect the steps, which I guess may be a good or bad thing. But greedy solutions are so tricky, not because they are difficult to prove the runtime, but because they are difficult to prove their correctness. And this solution is contingent on, I guess, a property of summations and maybe just logic that in a way is not simple to arrive to. And I'm not sure exactly how to train this sort of number theory muscle, if you will, to the point where it's ready for an interview question like this. But that's the explanation for at the high level of why we can disregard all those answers in the middle and immediately jump to the next index afterwards. And of course, we can also say that if our value, our sum from A to K, minus our cost from A to K is less than 0, And that was not so because it was not changed for the previous one. That means that K minus the gas that we got at K minus the cost that we got at K, the cost to go from K to K plus 1 is less than 0. And therefore we should remove it. And therefore, or rather, that cannot be a viable candidate. Because when we added it into our existing sum, that is when we pushed it over to the next, that's when we pushed it to less than 0. But there's probably a lot more within that explanation that I could talk about, or at least investigate into, that I just don't have time for today. But this will definitely be something that I come back to, especially with just like trying to make sure that the logic just is sound in my mind. But in any case, let's actually throw this through a submission. And there you go. I think having the constraint, the problem constraint of the length, though, is seriously a really big help in terms of discovering the approximate runtime that you need to solve one of these LeetCode problems. So maybe that's something for you to consider, but at the same time, I do see it. I am concerned about it being a bit of a crutch, being like, okay, the input size is this much. That means that it needs to run in this runtime, because I imagine that this is not necessarily something that will be a good question to ask within a technical interview, because I don't think that it's necessarily something that the interviewer will have in mind. And it might come off as being like, I need a hint in terms of the runtime. I'm not too sure about that, but that's just how it is. But yeah, maybe I'll reconsider looking at the input size, or maybe I won't, because I think that it's still a good way to sort of just gauge like sort of my understanding of like, okay, if I know at least this much, then how far can I get, right? But yeah, that's the solution for LeetCode number 134, gas station. A greedy solution with, again, really weird explanation. This one and container with most water, man. I'm starting to really dislike greedy solutions, primarily because they're just so damn hard to prove. At least in a short amount of time, right? But in any case, I hope you learned something, and I'll see you for the next problem.